Okay, hello class. Welcome back. In this video, we're going to be exploring a little bit about optimization, and we're going to be doing one problem involving a box. So the first question I want to address is, what is optimization? And to optimize really means to find the biggest or smallest quantity of something. So let's write that in. So I just took a little break real quick and went ahead and wrote that out. Optimizing simply means to find the biggest or smallest quantity. In calculus, it's going to mean to find the absolute max or the absolute minimum of a quantity. So let's write that out. In calculus, optimizing a quantity will mean to find the absolute max or min of a quantity. Now, the quantities we'll be optimizing, which means to find the max or min, will be things like volume. It will be area, perhaps. It might be perimeter. It might be weight. It might be time. It might be cost. These are all things that can be optimized. Speed or velocity. And I even have magnitude, so the size of something. So all of these are quantities that can be part of an example. Okay, so what I'm going to do now is go ahead and clear these annotations, and I'm just going to go ahead and scroll down so that we can focus on this problem. It says a vendor needs you to create a box with no lid from a 9-inch by 12-inch piece of cardstock by cutting congruent squares from each corner. How large should the squares be to ensure the box holds as much as possible? How much will the box hold? So here's the thing. We first have to identify the question. And there's actually two in this problem. It says the question is going to be, how large should the squares be cut to ensure the box holds as much as possible? So when they ask how large or how big should the squares be, they're really asking us for the dimensions of the squares. And a square is the length and the width are the same size. So really it wants to know what are the sides of that square in order to have a box that holds as much as possible. Well, if you think of a box, the stuff that goes inside it, that's known as the volume. So they want us to tell how big the squares that you're cutting out of this piece of cardstock are going to be so that we can get the max volume. Let me write that down. And then it says, how much will that hold? So how much will it hold? So they're asking two things. How big is the square and how much is that volume going to be? So what is the goal of the problem? The goal is to maximize volume by finding the dimensions of the square being cut out. Let's fit that here. Being cut from each corner. That's really the goal. Okay? And so we're going to go ahead and go through I have 5 steps really to solve this problem. And I'm going to go through each one with you. I've kind of separated my problem. I've set up the notes in that way so that you can see the different steps. So let me just clear these annotations. And again, remember, you can pause this video at any time you need to so that you are able to copy notes, process, or replay certain parts of it if needed. So let me see. Let me set this up nice and easy here. Okay. Step one in all of these problems is to try to draw a picture, and label everything. Sometimes a picture is not necessary, but sometimes it really does help. So step 1 is to go ahead and draw pictures. if possible, and label everything. It's kind of the same as related rates in that way. Okay. So I've done that right here in step 1. I've drawn a picture. Now, I want to draw some dotted lines here because I want you to see what we started out with. So before we cut this square out, this was actually a paper that looked like this, something like this. And what we basically did was we cut those squares out. And this paper was supposed to be a 9 by 12 paper. That's what the problem said. So that means that's 9. And from here all the way out to here is going to be 12. Okay? But what we did is that we cut out those squares. So I'm going to use a little eraser here to kind of erase those. Notice that the squares are the same size. They're congruent squares from every corner. And our job is going to be to find what size do those squares need to be so that we get the biggest volume possible. So let's go ahead and label some things. Now, remember, if you fold this these flaps up, first of all, the height of the box is going to be determined by the size that you cut out, the side of that rectangle or square, excuse me. So when you fold this flap up, fold this flap up, this flap up, this flap up, and you tape all the sides, it's supposed to kind of look like a box like this. The height of the box is going to be given by how much, how big that square was, the side of that square. So this is actually the edge of the square. That's the same dimension. When you think about it, if this whole thing was 12 and we took away two squares, those squares, we don't know what they are. So we're going to just call those X right now. All right. And if one side is X, the other one's X. We don't know how big. We're going to cut those out. So those are variables. The X's here and here. And then this is an X as well. Well, if you have 12 from the start of the paper to the end of the paper, but you cut out 2 X's, what's left over here is going to be 12 minus 2X because you've taken off 2 X's. And this side is going to be 9 minus X and X. That's 9 minus 2X. So again, the whole thing is 9, but this little chunk has to be 9 minus 2X. Okay, cool. So what? That's us labeling everything. Let's move on to the next step. The next step is to find a feasible domain. Now, what that means is we're looking for how big of an X, how big of a box we're going to cut out. So in essence, how big this X is going to be. And if you think about it, we have to go with the shortest side because whatever you cut this way, whatever you cut here, you're going to have to cut on this side. So we're going to focus on the shortest side. And if you think about it, since we have to cut X from the top here and the bottom, the most we can cut is going to be 4.5 this way and 4.5 from the bottom up. And at that point, what we'll have is just 2 pieces of paper. We won't be able to make a box. So for our domain, for X, we know the least we can cut is 0. If we don't cut anything, we're just going to have a flat sheet of paper. And then the most we can cut is 4.5. If we go with 6, thinking about this guy, well, there's no way we can cut 6 here and 6 here because that exceeds 9. So that's why we have to go with the shortest side. So our answer is going to be between 0 and 4.5. That's not for the volume. That's just for the side of the square. So now we need to create an equation for the quantity that we're trying to optimize. So our step 3 is to create equation. And I'm going to add the stipulation that you need to make sure you have only one variable. If you don't, you're going to need some secondary equation to sort of fix that. So we're going to go ahead and create an equation. If you remember from above, our goal was to maximize the volume. And we needed to find the size of the square that was going to accomplish that. So I need an equation for volume. And in this case, this volume is going to be in terms of X because that's the variable we're using. Now, normally, the volume is of a box is length times width times height. So let's use this block to try to understand. So this height here is going to be X because that's the flap folded up. This here, I imagine, is the short side, which is going to be 9 minus 2x. And this is the long side, which is going to be 12 minus 2x. So instead of using L times W times H, we're going to use these expressions that we've set up prior. And we're going to say, hey, the length times the width times the height. Again, the order doesn't matter because it's multiplication. So I'm going to go ahead and take x, and I'm going to multiply it by 9 minus 2x. And I'm going to multiply that by 12 minus 2x, making sure I have parentheses in each of those. And this is my volume equation, okay? This is often one of the harder steps, but for this particular problem, we know it's volume. The hard part is that you just really have to label everything correctly and understand what each piece is. So step 4 is to find and test CPs and test endpoints if applicable. Well, our endpoints are 0 and 4.5, and we already know those are not going to be the answer. So we're hoping that we're going to find a CP in between that'll work. So find CPs and test. Okay. All right. Now, at this point, you have a choice. You can FOIL this out, distribute the x, take the derivative by hand, set it equal to 0. That's how you find the critical points, and do your chart. But I'm going to show you a little bit of a shortcut. If you have a graphing calculator, you can actually ask the calculator to graph the derivative of this function, and it will tell you the CPs. I don't have a graphing calculator, but I do have Desmos, and I'm going to show you how to do it there. But remember, you won't have Desmos on the AP test, at least not yet. So you're going to have to make sure you can do it on the graphing calculator as well. Okay, so what I have here is I've kind of already entered my functions, but I want to show you how I did that. If you just click on that spot and go to functions, you're going to have to go to miscellaneous. In miscellaneous, you see DDX, and you can press that. I'll show you here in a little bit. You can press that, and then you would basically enter your function. Okay, that's what I've already done here. I've entered the function x, 12 minus 2x, 9 minus 2x. Remember, this is the volume of the box, and we want to maximize the volume, so we're going to go ahead and find the CPs. Now, just so we keep things in your graphing calculator, on in your graphing section, like Y1, you would enter it exactly like this. And in the spot where it asks you for what x value, you would just type in x. And I can show you in class how to do that. But for now, I'm going to use Desmos. I'm going to go to my settings, and it says x-axis negative 7.5. I'm just going to put 0 because I know that my smallest answer would be 0 and my biggest answer would be 4.5. In your calculator, that would be your x-min and your x-max. All right, and I just did that because I know that I don't care about anything besides that. All right, I'm going to go ahead and graph this function. It's not going to graph the volume. It's going to graph the derivative. Okay, and I see that I have one critical point right here. Okay, so as I said earlier, we have one critical point right here. If you were to distribute everything and then take the derivative by hand with the power rule, this is what you would get. And I'm going to go ahead and graph that so you can see that it comes out to the same thing. So you see the purple line graphed right on top of, or the purple curve graphed right on top of the orange curve. So whether you ask Desmos to compute the derivative for you, or you compute it by hand, you can see here that you get the same graph. So if I just hover over this, and in your calculator you would have to do second calc zeros to find the 0 of this function, you can see here that I got a CP of 1.697. Okay, and that's what we're going to use in a moment to solve the problem. Now, before this critical point, this is the derivative. You notice it's located above the x-axis, so that's positive, and afterwards it's going to be negative. So I can really build my chart off of this quite easily. So what I did now is I came back in step 4, which is to find CPs and test. My CP, the only one I got was 1.697. I know the derivative was positive and then changed to negative, so that means it was going up and going down. Since we're trying to maximize, again, we don't really need to check the endpoints. I know both of those are mins. The only max I'm going to have here is 1.67. So the box needs to be 1.697 by 1.697. The last step is going to be to interpret my solution. If you remember, my question was not only to find the x, but to find the volume. So I'm going to take this x and plug it into my original equation and go ahead and find the volume. So I have my answer here. As you can see, my box is going to be 1.697 by 1.697, and my volume when you plug it in is